From the NASA Mission Directors Center at Vandenberg Air Force Base in California, this is Delta Launch Control.
Inside that rocket, about to blast off into space, are 6 satellites. And they will join thousands of other satellites in orbit around our planet. Part of the latest technology that we take completely for granted. But I want to change that. I want to re-examine what these masterpieces of engineering are doing for us. My name is Maggie Adair-Pocock, and I'm mad about satellites. In fact, I help make them. For the last few years, I've been working on the most ambitious satellite ever, the James Webb Space Telescope. Now, I want to find out how these awe-inspiring machines have come to fill our skies. Seeing how 50 years of satellite research has pushed at the boundaries of technology, and how this has transformed our world.
5, 4, 3, 2, main engine start, 1, 0, and liftoff of the Delta II with the NPP satellite.
This is the story of how satellites have changed all aspects of our lives in ways that you can imagine and many you can't. It's 6:30 a.m, an average day in an average house. But while we sleep, how many of us know our lives rely on extraordinary machines, keeping an eye on us from space? They influence time, tuning our clocks. As I settle down for breakfast, a satellite beams the signal to my television. At least 3 more make a live link to the other side of the world. And a further 4 allow the Met Office to forecast the British weather. These satellites aren't so surprising. You probably know about them already. But what about the hundreds you don't? Satellites that helped harvest the wheat for my husband's cereal, deliver his milk, or chose where to brew the coffee he's spilling. Others manage our water, overseeing flood control and surges of power in the national grid. Once in my car, everybody recognises a sat-nav. But what about the fuel I use? My lottery ticket? Even the train I catch, all increasingly depend on satellites. Trains, planes and automobiles, shipping, cereals and flooding. It's not even 9 in the morning and already I've used nearly 40 satellites. These are the satellites that have changed our lives. But what about those that are changing our understanding of the universe? This is a full-scale model of the James Webb Space Telescope. When the real thing is launched around 2018, it will be the largest, most powerful satellite telescope ever built. With it, we'll be able to see wider, deeper, and more clearly into space than ever before. We may even be able to look back to the very birth of the universe. For several years, my job has been to work on the special cameras that will allow the James Webb to peer deep into the cosmos. By capturing images of stars 13 billion light years away, it'll look back in time, helping reveal how the universe itself was created. I believe that James Webb and the countless satellites that dominate our day are amongst the greatest scientific achievements of our age and sit at the cutting edge of technology. We're going to look at the breakthroughs that make this remarkable machine possible. What were the scientific challenges that were faced in the satellite revolution? And in the early days, there was one problem above all that space scientists wanted to solve. How do you get something, anything, to hover in space above the Earth? Well, a good place to answer that question is here, by this lake. A beautiful spot to try and launch my own satellite. Three, 2, 1. Fire! The force of gravity has, of course, pulled my wannabe satellite back to Earth. What goes up always comes down. Or does it? As we all know, the Earth is round. And that means, as we travel over the surface, it gently curves away from us. Now, if we can travel fast enough, something miraculous happens. We keep on falling, but we never hit the ground. Let's imagine that I can launch this orange at incredible speeds. It's something Sir Isaac Newton noticed 300 years ago. Relative to something moving horizontally, the curve of the Earth makes the ground beneath drop away. If my orange, or anything else, can move fast enough, it can stay ahead of that curve and effectively outrun gravity. It'll never fall to Earth. Because the curvature of the Earth is quite slight, you need to be travelling at around 8,000 metres per second to compensate for the pull of the Earth's gravity. If you can reach this speed, you're now travelling around the Earth rather than down towards it. Not easy, of course, when there's air resistance to slow you down and obstacles to get in the way. But once you get above the mountains and most of the atmosphere, let's say 300 kilometres up, you are now in space. And if you can keep your ball travelling fast enough, you can stay ahead of the curve. You're in orbit. Well, that's the theory. But it took 250 years after Newton's death before anyone built a machine powerful enough to put it into practice. In 1957, a Russian rocket carried the first man-made object into orbit above the Earth. No bigger than a beach ball, Sputnik stayed in orbit for 3 months. For the Soviet Union, it was a massive propaganda victory. And the beep of its tiny radio transmitter fired the starting gun for the space race. I have always assumed that as Sputnik was dragged into a lower and lower orbit, it got hotter and hotter due to the Earth's atmosphere and was eventually completely burnt up. But surprisingly, a small piece of that epic spacecraft is kept here at the Smithsonian National Air and Space Museum. So I hear you have a bit of Sputnik actually here on site.
We do indeed. We have something that is called the firing pin, which is a relatively small object that is not really a firing pin in any real sense of the term. That implies that you launch a rocket by turning a key or something. But what it really was a small metal object that fit into the Sputnik spacecraft. And when you were ready to start the system inside that was run by batteries, you could pull this out and it would complete the circuit that would allow the power systems to start to operate.
So it's like when I buy a little toy, sometimes they have a little plastic tag, pull it out and the batteries start working.
That's essentially what it was.
The firing pin is a tangible reminder of who won the race into space. It may be small, but to me, it is a priceless relic, which, by making the connection between the battery and the transmitter, unlocked the age of satellites. But it wasn't easy. Desperate to catch up in the space race, it took the Americans years of rocket research. And numerous false starts. Before finally, they successfully launched their first satellite, Explorer 1. In 1959, Explorer 6 was the first satellite to take a picture of the Earth. It doesn't look like much, but this is a silicon chip. But not any old chip. When this device was invented, it totally revolutionized the world of spy satellites. It's called a charge-coupled device, a CCD. At its heart is a thin sheet of silicon, which has an unusual property. It's sensitive to light. So if a passing photon hits it, it takes that photon and creates an electron, which can then be stored. This means it can generate a picture of anything that's in its field of view. It changed the rules of the game. The invention of the CCD in the 1970s allowed satellites to take pictures, store them electronically, then transmit them back to Earth using radio waves. Today, intelligence agencies don't reveal how powerful their spy satellites are, but some details have leaked out. In 2007, it was revealed US satellites had been targeting American territory. In fact, the Super Bowl. US counterterrorism wanted to monitor potential internal threats. The real photographs have never been released. They're just too sensitive. But it shows the resolution is now powerful enough to see objects and individuals down to a few centimeters. But spying was just the start, because civilian scientists also began using this new imaging technology, transforming our knowledge of the Earth. It led, of course, to breakthroughs in our understanding of the weather, the shrinking of the ice caps, and the effect of cities on our environment. Images that have revealed the full wonder of our planet. Today, satellite images are everywhere and available to anyone at the click of a mouse or the touch of a phone. CCDs have transformed not only what we take in when we look down at our planet, but also what we see when we face outwards. This will be James Webb's task when it's launched in 2018. It'll be glimpsing galaxies that are almost unimaginably distant, 13 billion light years away. How do you capture the intimate detail of a galaxy spread over millions of light years? Well, the vital component for the James Webb is its gigantic golden mirror. And it's not just size. To see into the depths of space, scientists have had to take mirror technology to a remarkable new level. One part above all, is crucial for the mirrors on space telescopes. Their coating. This is what does the actual reflecting.
And something else flashing over there.
I am with a group of brownies trying to spot satellites in the early evening sky.
Now, we don't just look this way, we've got to look all across the sky. We've got to try and take it all in.
I can see the moon, but I can see two of them.
On average, 2 satellites pass over Britain every quarter of an hour. But they're not the easiest things to see.
Now, what are you looking for? Well, you're looking for something that looks a bit like an aeroplane, but it's not going to flash, and it's going to move slowly across the sky.
Tonight, my team of brownies is in for a treat. Because the biggest satellite of them all is due to pass directly over Hatfield. It's the International Space Station, the largest thing human beings have ever put into orbit. It took more than 12 years and 30 trips to build, and it circles the Earth nearly 16 times a day. Everyone, including the astronomers with their telescopes, is waiting for it to appear over the horizon.
Whoa, I can see a star moving really, really quickly.
Oh, no, see, I don't think that's a star moving, that's the space station.
I can see it.
That is the International Space Station.
There's a crude rule of thumb. If a satellite orbits 300 kilometres up, it needs to be just 1 square metre for us to see it with the naked eye. The ISS has 8 solar arrays, each 70 metres long. So with a pair of binoculars, you can see it from Earth in wonderful detail.
You will do anything else.
Whoa.
That's still the space station. So it's gone all the way from over there, up above our heads, and now it's heading over there. And you can see it's still moving slowly.
It's like a rocket.
Like many satellites, the ISS is only visible for a few minutes before it disappears over the horizon.
I think it's gone now.
Oh.
But see, I know, but at least we saw it.
In the early days of satellites, this vanishing act was as frustrating to their engineers and controllers as it was for our brownies. It meant that the opportunity to transmit a signal, like a television picture, back to a particular point on Earth was very brief, maybe only lasting a few minutes. So the dream of the first satellite engineers was to have a satellite that stayed stationary above a single point on the Earth, allowing them to transmit information whenever they wanted.
So how do you keep an orbiting satellite hovering above a single point over a rotating planet? Well, it seems simple. You just slow your satellite down until it's above the point you want. But unfortunately, it's a lot harder than it sounds. And to show you, I'm going to use this carousel.
Imagine it's the Earth, spinning on its axis. And let's say I'm a satellite, orbiting it. If I start slowing down to be above just one place, I'm not going fast enough to stay in orbit. So I start spiralling down towards the Earth. And eventually, I burn up in the atmosphere.
There is a solution. The further I get away from the Earth, the weaker the effect of gravity, the less it pulls me back. And there is a magical point where the force of gravity is so weak that I can travel fast enough to stay in orbit, but also slowly enough to match the speed of a single point on the Earth's surface below.
Scientists calculated that this is nearly 36,000 kilometres away. Orbit here, and you can stay above the same point on Earth.
You are now in a geostationary orbit. And when this was first achieved, it triggered a revolution. Because now, any time, day or night, you can beam information back to Earth. This was the birth of the communication satellite.
It meant that with as few as 3 geostationary satellites, you could beam a signal around the planet, broadcasting it to almost anyone. The first satellite to relay a television signal was Telstar in 1962.
Here we are. There's a bar. Now, we are anticipating... That's a man's face. There it is. There it is.
Its first broadcast lasted just 19 minutes. But within a few years, a network of geostationary satellites meant live communication was possible anytime or any place on Earth.
In the end, when there are more satellites still, you'll have television and telephones all over the globe, a shattering thought.
Broadcast television had created a global living room with shared experiences and values.
Challenger, go with throttle up.
It also meant that as well as recording events, satellite broadcasts were now helping to cause them. Like the protests in Tiananmen Square, the fall of the Berlin Wall, or the Arab Spring. Today, nearly 200 communication satellites are broadcasting back to Earth, most in geostationary orbit. But staying 35,786 kilometres above a single place on Earth isn't easy. Satellites tend to drift. So to keep them in position, you need a technology that reached its pinnacle with Saturn V. The most powerful rocket ever built. But rocket thrusters don't all need to be like this. To keep a satellite like the James Webb in orbit, for instance, you need thruster technology that's far more precise. Despite being the size of a tennis court and weighing over 6 tons, the James Webb Space Telescope will use microthrusters the size of a coffee cup. How is this possible? Well, it's due to the microgravity vacuum environment of space. With virtually no air resistance or drag, it can take a tiny force to move a very large object. Engineers here at the Massachusetts Institute of Technology are at the cutting edge of thruster engineering, taking them to a new level of precision. Here in the lab, they've got an unusual way of recreating the frictionless conditions of space. They're using a tabletop and mini satellites called spheres.
We have a very smooth surface, and we also have these air carriages, which are little structures that we put underneath the satellite that have CO2 attached to them in these tanks, and we use them a lot like an air hockey table.
So can I see them in action?
Sure, absolutely. And so your job is going to be to fly this satellite, which is sitting right here, all the way over and dock with this satellite.
I'm not a very good games player, so I'm a bit nervous now. Let me put this down here.
Okay, twist the controller.
Whoa! The microthrusters on the spheres shoot compressed carbon dioxide. It's colourless, but strips of tinsel show when they're firing. So that would give me some twist?
Yes, exactly.
So I could do a dance.
Yes, exactly.
Trying to... Okay. Now which way?
Okay.
Look, wrong way.
One of the other hard things to figure out which
because as
way.
I spin, I lose my orientation. Oh, yeah, and it just keeps on going, doesn't it? Uh-oh. Fire a thruster, and just like in space, your satellite shoots off in the opposite direction, with nothing to stop it. Imagine how hard it is in 3 dimensions. So far, they've tested the spheres on board the ISS. It shows that their thrusters are so precise, the spheres can fly in close formation. The next step is to build satellites that can do this in open orbit.
There you go. That's a good trajectory. Now, don't build up too much speed there. Hooray!
DOS! This ability to keep satellites in one position and know where they are is now remarkably accurate. But it's had a surprising side effect, because it means we can also know our position extremely accurately. The story begins back in 1957, shortly after Sputnik was sent into orbit. The sound of any object changes as it moves past us. While Sputnik was orbiting, American scientists realized they could use this knowledge to locate it, listening to the changing sound of its beep as it moved overhead. It got scientists thinking. If you could work out the position of a satellite from here on the ground, could you reverse the process? Could you use the satellite's known location to find your unknown one? The result was the Global Positioning System, or GPS. And how it works is simpler than you'd think. It's all due to one of these. The breakthrough technology that led to GPS was actually a clock, but not any old ticker. This is an atomic clock, the most accurate timekeeping device ever built. For instance, if I set one of these going at the time of the Big Bang and let it run through, we would now know the age of the universe to within a few days. Now, compare that with a quartz watch, and we'll be out by 150,000 years. Atomic clocks are so crucial to GPS because the first stage in working out your position using a satellite is to know exactly where the satellite is. And the best way to do that is using time. Each GPS satellite broadcasts a signal with a timestamp. It takes the signal just a fraction of a second to travel to your GPS receiver back on Earth. When it arrives, the receiver's clock works out how much earlier the signal was sent. Knowing this time difference means it can then work out how long it's taken to arrive, and so how far away the satellite is. But it doesn't just do this for one satellite, it does it for at least 4. Having calculated how far away each is, your receiver then creates spheres of distance around you. And where they intersect is where you are. There are 31 GPS satellites in all, and the more you are in contact with, the more accurate your reading. It means wherever we are in the world, GPS can tell us our position within a few meters. Satellites are no longer just for big governments and powerful corporations. They're becoming almost personal. And tonight, I've got a front row seat to discover how. Here, in the Vandenberg Air Force Base in California, scientists are taking the next leap forward in satellite technology. Inside the tip of the rocket, situated over there, are some of the first new prototypes in the personal satellite revolution. They're called CubeSats, and they look like this. 5 of these satellites will all be released into orbit, hundreds of miles above our heads, like a flock of strange alien birds circling the Earth. They're owned mostly by universities and will join the 40 or so other CubeSats already in orbit. They do everything from measuring radiation in the solar system to studying bacteria in space. Surprisingly, one country at the forefront of CubeSat technology is Britain. Here, engineers have devised one of the most imaginative uses for them so far.
That bit in the centre is the CubeSat. So do all of CubeSats have these sails as well?
This is a particular mission. It's called CubeSail. One of the big hot topics at the moment is space debris. Yes. Okay, there's lots of debris up in space. So if we can attach these CubeSats to bits of debris, maybe they be old satellites or old parts of launchers which are still orbiting up there. If we can attach these CubeSats to them, open up the solar sails and allow them to literally drag them back into orbit and burn up in a safe manner, it means we're decluttering space.
Because I must admit, one of my fears with CubeSats is the idea of all these sort of little things floating around in space causing more space debris. But this is actually helping to solve the problem.
Yes, very much so indeed.
Yeah, very neat.
Thank you.
CubeSats all rely on the same basic components, much like the different parts of a PC. Here in Surrey, they're taking this to an extreme. Dr. Peter Shaw shows me how they're currently building a satellite around the smallest and most popular computer that exists today, the smartphone.
So our modern day smartphone, a couple £100 from the high street, okay, is a very capable device, okay? It's got cameras on there, it's got storage, gigabytes worth of storage, okay? It's got processors, very advanced processors. It's got accelerometers.
Ah, so the accelerometers are things that orientate the screen so you get a direction.
Yeah, and we can use those sensors in our spacecraft. Okay, so the whole idea in the future is to get rid of all of these components and replace them with a mobile phone. So this is the internal structure of the CubeSat itself, where we'll mount everything onto.
Often when I think of sort of space science, you think of sort of huge companies with really big budgets. And although this isn't sort of cheap, you could almost do it in your your garden shed.
Yes, certainly, if you had a bit of money, I must admit. But no. Compared to other satellites, for instance, the big communication satellites, you're talking £500–600 million.
Yes.
If you're talking about satellites the size of a washing machine, you're talking about £10–15 million.
So how much does this cost?
All in all, you could probably put a whole mission together for about £80,000.
It seems to me that in the future, satellites will increasingly provide customised services for small groups of people, even individuals. They'll allow imaging, communication, and exploration at a whole new personalised level. Over the last half-century, satellites have transformed the way we lead our lives. But I feel we are now on the launch pad of a second satellite revolution. And it's one whose impact could be even more profound. The age of the personal satellite.
2, main engine start, 1, 0, and liftoff.
My God, that's amazing. It's so bright.